All right, greetings everyone. Welcome to the third part of the video for section 8.4. And as promised in this video, we'll look at converting between the different ways of representing a vector and then also do an application problem. So here we're asked to find the components of a vector, a vector with magnitude 10, and that's at an angle of 30 degrees measured in standard position. Now we're not given a name for this vector, but I'm going to call it vector u. And this information here that we're told that the magnitude of the vector is 10 tells us the magnitude of the vector u is 10 units, whatever the units are in this case. Okay. And notice again, as I mentioned before, here I'm using these absolute value type symbols around the name of the vector to indicate that I'm talking about the magnitude. Remember, it is not correct when you're talking about magnitude to write something like this. Okay, u equals 10 units. That is not the same thing. All right, so we need to find the components, which means we need to find the x and y components, so the horizontal and vertical components. And you may recall from earlier in this section that we have some formulas for these, right? So the x component is given by doing the magnitude of the vector times the cosine of the angle. And the y component is given by doing the magnitude of the vector times the sine of the angle. And if you also remember these formulas, even though they look kind of new, they're very similar to the x equals r cosine and y equals r sine that we had with polar coordinates. So in this case, we'll just plug in the different values we have. So the magnitude is 10 times the cosine of the angle, which is 30 degrees. And then again, the magnitude of u is 10 times the sine of the 30 degrees. Plug in those values, so 10 times cosine of 30 degrees is root 3 over 2. Sine of 30 degrees is 1/2. If we multiply here, the 2 can reduce to a 1, and the 10 becomes 5. So we get 5 root 3 as the x component, and then 10 times 1/2 gives us 5 as the y component. And so the vector here, its x and y components will be 5 root 3, comma 5, okay, in those pointy brackets. All right. Now we can also just kind of do an eye test to see if this makes sense. I'm going to draw a little coordinate axis down here. So if we have a vector that has an angle of 30 degrees, that means it starts from the positive part of the horizontal axis here, rotates just 30 degrees around, and then it would have a magnitude of 10 units, whatever that looks like. So this would be our vector u. And notice that its terminal point there would be in the first quadrant, which is where 5 root 3, 5 is. So this makes sense. Okay. All right. Let's take a look at converting the other way. So now we're given the components of the vector. We're told that they are -4, 3. And we're asked to find the magnitude and the angle of the vector. And recall, we're going to find the angle measured from standard position. We'll also do it in degrees, which is common practice with vectors. So this time I'm kind of going to work backwards. I'm actually going to draw my picture first. So we're told that the x and y components are -4 and 3, which means that if we place the initial point of our vector at the origin, we're going to go 4 units to the left since our x component is negative, and then up 3 units since our y component is positive, which should give us a terminal point here. So this is what our vector would look like. Vector kind of pointing in the northwesterly direction. Okay, we need to find the magnitude of this vector as well as its angle. So I'm going to call this vector v. We'll start by finding the magnitude of v. And if you recall from a picture we had before, if this is our vector, well, the x component goes along here, the y component goes along here, and then the magnitude is kind of like the hypotenuse of the right triangle that is formed, which means that to find our magnitude from our x and y components, we can use the Pythagorean theorem. So what we can do is that x squared plus y squared, so the x component squared, the horizontal component squared, plus the vertical component squared, equals the magnitude of the vector squared. Plug in the information we have. So magnitude squared equals -4 squared plus 3 squared. Give us 16 plus 9 equals the magnitude of v squared. Because the magnitude of v squared equals 25. Take our square root on both sides. Should give us the magnitude of v is equal to 5 units, whatever our units are. Okay, so that would be our magnitude. All right, so I'm gonna write that off to the side here. So the magnitude of the vector, again, is 5 units. And now we need to find the angle of the vector. So how much it is rotated from standard position. And again, we're going to kind of hark back to what we did with polar coordinates, right? So this angle is going to be kind of like this here. That'll be our angle theta. And since we have an x and a y point, or the x and y components, we could set up an equation as, say, tangent of theta equals the y component, which is 3, over the x component, which is -4. And from there, we could do inverse tan, or arctan, to find the angle. When we do that in this case, we end up with -36.8699 degrees, which you probably agree with me is definitely not going to give us the angle in our picture, especially because our vector is in the second quadrant. And in fact, if we remember again how arctan works, we know that it only gives us answers in the first or the fourth quadrant. And since this angle we've gotten is negative, we know it's going to be down here in the fourth quadrant. And so we use its reference angle, which would be the angle it forms here with the horizontal, which in this case will be positive 36.8699 degrees. And we use that as a reference angle to find the corresponding angle in the second quadrant. So we know our angle's got to be up here. It's got to have the same reference angle as that one down there. So that's the 36.8699 degrees. We know that's it's going to be that much less than 180. So to find the angle we need, we can do 180 minus that angle. And we do that, we end up with 143.130 degrees. Okay, so that'll be our angle theta. Oops, it's not that color though. That will be our angle theta for this vector. So it's got a magnitude of 5 units, and it's at an angle of 143.130 degrees. Okay. All right, let's look at one more example in this video. So we're told that a force of 30 pounds is applied to a rope tied to an object, and that the rope forms a 20-degree angle with the ground. I'm going to figure out how much force is acting horizontally on the object. Be another one of those great opportunities. Looks like, maybe let's just say it's that. Here's the rope coming up. Okay. And we know that this rope, we're told, is forming a 20-degree angle with the ground. And then there's a force of 30 pounds acting on it. Now, I'm going to call the rope a vector representing the rope, okay, because obviously we're going to use vectors here. I'm going to call that R. And what do you think that force of 30 pounds is representing about that vector? That's right. It is our magnitude of the vector. So as I mentioned at the beginning of this section, vectors can represent lots of different things. Their lengths or their magnitudes can represent lots of different things. It's not always actually physical length. So in this case, it's representing a force. So we know the magnitude of R is 20 pounds. If we want to figure out how much force is acting horizontally, we have to keep in mind that in physics, we can break forces down into a force going the horizontal direction as well as one going the vertical direction. And as you might imagine, if we think of the force as a vector, then those are going to correspond to our x and y components. So how are we going to find the horizontal force here? Well, we'll just use our formula for the x component of a vector, which remember is given by the magnitude of the vector times the cosine, whoops, not equals, times the cosine of its angle. So in this case, we would have our magnitude, which is 30, times the cosine of our angle, which is cosine of 20 degrees. Plop that in the calculator. It gives us 28.191 as the horizontal component. And this, in this case, is going to have the same units as the magnitude of the vector. So it would be 28.191 pounds acting in that horizontal direction. All right. Great. That's it for now. Thank you for watching.